So after this, after the CNN, after the convolutional neural network, we'll be left with 3 more chapters. And all right. So today we are going to cover convolutional neural network, and this is a very important chapter. And the CNN, we'll use CNN to pronounce it quickly. CNN is at the heart of most of the image recognition or the object identification in the videos, in the photos, and so on. So there are many more use cases of CNN that we think about. So CNNs are quite important. So all right, and all right, let me just give you the slides also. Thank you for that reminder. All right, so great, great. All right, so should we start, or do you have questions before we move to the topic? All right, so let's start. Great, great. A question from Minta is, what about projects? So yes, we will discuss the project after this. Okay, and yes, because so far what we learned was the foundation of the neural network. Now let's utilize whatever we learned in the previous 2 chapters. So the training models was really important chapter, and before that we learned about basics of neural network, and before that we learned about TensorFlow. So after the CNN, you will be ready to handle a lot of image or video or similar projects. And so so the accuracy of the same MNIST, we are going to use the same MNIST project in this particular chapter, and we'll notice that the accuracy of the same project is going to shoot up to beyond 99%. All right, so let's start. Even though in 1996 IBM's Deep Blue computer beat the world chess champion Garry Kasparov, but but still the computers were not able to do very trivial tasks such as detecting a puppy in a picture or recognizing spoken words without being specifically programmed to do so. This was until quite recently, and earlier we had to basically do a lot of programming to get the same work done. But now, and the performance wasn't great. So until quite recently, that was the very trivial tasks which humans or animals could do wasn't possible for computers to do. And this revolution has mainly occurred because of CNNs. So CNNs emerged from the study of the brain's visual cortex, and they have been used in image recognition since 1980s. In the last few years, the CNNs have emerged to achieve superhuman performance on some complex visual tasks, and all this was possible because of increase in computational power, the amount of available training data, and the tricks presented in the last chapter on training deep neural networks. So we discussed various optimizers and various initialization techniques. So because of algorithmic improvements along with the computational power, along with a lot of data, along with ability to manage a lot of data as well, this revolution has been possible. This revolution has been possible. Now, today CNNs power the image search services, self-driving car, the the video classification systems, the voice recognition systems, and NLP, natural language processing. So so you can realize the importance of CNN by these examples. And in this chapter, we will present where CNNs came from, what their building blocks look like, and how to implement them using TensorFlow. And then we will present some of the best CNNs architectures. So let's look at the architecture of the visual cortex. In 1958 and 1959, David H. Hubel and Torsten Wiesel performed a series of experiments on cats and later on monkeys. These experiments gave crucial insights on structure of the visual cortex. These experiments showed that many neurons in the visual cortex have a small receptive field, meaning they react to visual stimuli located in a limited region of the visual field, meaning that the the neurons in the visual cortex basically were mapped to an area physically. There was basically, I think this diagram will make it more clear. So neurons were mapped to the area in the physical cortex. So they basically prove this point that if a particular neuron is dead in the visual cortex, then this portion, a particular dark spots would occur. Okay, so this was basically their experiments the with the experiments on cats and later on monkeys. So they specifically uh, proved that neurons in the visual cortex, okay, neurons in the visual cortex responded to a small local receptive field. Okay, so this was a very basic, very um, foundational research in the domain of the neural sciences. But while implementing the similar image recognition system, the researchers found this research to be very relevant. All right, because CNNs is actually organized like this. Now, so next question is, why not simply use a regular? Now let me just go ahead. Now, to recognize images, we are going to use a similar technique like the one that is presented by the researchers, and we're going to use a similar way, meaning we'll create an input layer. input layer of neurons. Each neuron will map to the first layer will map to the one that is in the visual cortex will map to an area on the image. All right, that's what we are going to do as part of CNN. I'll describe it in more details. So this is what we are going to do. Now, question is, why not just use the deep neural network, the one that we created earlier? Just like that, why do we need the CNN as such? We could have just use we could have just used the huge fully connected layers for image recognition tasks as well, and it did give us good performance, but we could not go beyond a certain performance. All right, why is that? Why do we require CNN over a deep fully connected ones? The deep neural network works fine for small images like MNIST, where there were only 28 pixel by 28 pixel image. So the the neural network, that the fully connected one that we studied earlier, they basically is great for small images, but they break for larger images because if you remember the number of weights, the number of weights become really too many. For example, if the image was say 100 by 100, so the total number of pixels will be 10,000. The input layer will be of 10,000 size. If the first hidden layer is of 1,000 neurons, which means 1,000 multiplied by 10,000, those many connections, right? That is 10,000. That too in the first layer. This will require a lot of computing power. So CNN solved this problem by using partially connected layers. Instead of connecting everything from the first layer to the hidden layer, you will see that we're basically connecting things partially. All right, so this is what we are going to learn today. So there's an idea called convolutional layer, convolutional layer. All right, now this is a very important point. It is the most important building block of CNN, the convolutional layer. We'll connect the dots again. We're just going with one definition at a time. So it is the most important building block of CNN, and the neurons in the first input layer. So unlike converting an image from 2D to 1D, like the way we did in fully connected cases. So unlike the, the usual neural network where we connected the image into a single dimension one, here in case of CNN, we keep the image in 2D. Okay, in 2D. All right. Now we have something called a concept called convolutional layer. So the neurons in the first convolution layer are not connected here, are not connected to every single pixel. Okay, instead, but only to the receptive fields. Okay, just like the research. So every neuron in the convolution layer is mapped to an area, like this one is connected to only this one. This, or you can say in other words, this particular neuron is the result of the activation, or the value of this particular neuron is going to be because of only this particular area, right? Unlike the previous one where every neuron was a function of all the neurons multiplied by certain weights. Here, every neuron is a result of a small rectangle in the input layer. Okay, so you can see there is here we are just showing you two receptive fields. this is called a receptive fields. A receptive fields is converted into one single value. The value here of the neuron is a singular value created out of this particular rectangle. All right, so that's what we do. And once we have generated all such neurons, we take a receptive field. Let me reiterate, and I'm just jumping ahead a bit. We'll come back, and feel free to ask as many questions, because there would be many questions here. There would be difference of terminologies, so we all need to be on the same terminology. Okay, so input layer is called input layer, the way we always call. And since we are mapping an area in the input layer to a single pixel in this layer, we call this convolutional layer. There could be multiple such layers, and every pixel in the convolutional layer, every pixel in the convolutional layer is the result of a rectangle in the input layer. Okay, and this rectangle is called receptive field. All right, this rectangle is called field or receptive field. We will use F for this. Okay, so neurons in first layer are not connected to every. This is a very important point, because in the fully connected one, the result of each neuron, earlier what we the way we always thought of a layer was a one-dimensional layer. And right, a good question from Pratik. Pratik's question is convolutional network very specific to image recognition? Yes. So image, video, even audio, they have the same behavior as the so image, video, as well as audio. In all three, CNN have shown a great amount of performance. All right. All right. A question from Bintao. Why do we call it convolutional layer? Okay, so this process is called convolving. We are going to talk about a process called convolving, and then you'll get an idea. Okay, so basically this the way these pixels are going to be generated, that mechanism is called convolving, and that's why this is called convolutional layer. Now, so the neurons in the first layer, first convolutional layer, are not connected to every single pixel in the input image, but only to the pixels in the receptive field. Okay, so each pixel in this layer is a result of combining all of the pixels of a rectangle in the input image. All right. In turn, each neuron in the second layer, in the similar way, is mapped to a rectangle in the first layer. So for second layer, the first layer acts as an input, All right. So this architecture allows the network to concentrate on low-level features in the first hidden layer, and then assemble them into high-level features in the next hidden layer, and so on. All right. So basically, this kind of architecture allows the network to concentrate on low-level features in the first hidden layer, and then assemble them into higher level features in the next hidden layer. This point, I would like to make it clear after we go through the approach once, and then come back to this point, that why does this concentrate? Why does it concentrate on the high level features, and so on. So I think the meaning of why does it happen? Why is it able to extract the features and understand the features? we will learn as we go ahead with the process, then we'll come back to this point again, and then you will get the idea why does it work this way. Okay, or let me just give it a shot if I can explain right now. Okay, all right. So, all right. No, I think I'll come back again. So this kind of architecture basically works just like basically works on rectangles, which which might contain objects and therefore can extract the information and represent it like this. Okay. So essentially the idea of convolutional network is to behave just like the human or animal's visual cortex work. All right. So so it operates on the rectangles instead of linearly on all the pixels. All right. So if you think about it, this is more intuitive. This is more intuitive to us than than thinking about, say, our example of taking every pixel as a dimension while we were computing the MNIST, right? Remember our SGD example, whereby, or even the previous one, whereby every pixel of the image was a dimension, and we were basically computing the result by applying the weights on each pixel, right? So this is more intuitive because here we are operating on the rectangles. We are basically picking the sections of the image and then operating on it. All right. So this hierarchical structure is common in the real world images, which is one of the reasons why CNNs work well for image recognition tasks. Okay. Now, until now, all the multi-layer neural networks had layers composed of long line of neurons, and we had to flatten input image to one dimension before feeding it to the neural network, right? In case of MNIST example, we basically created an input layer with 784 neurons, and we converted the image into a linear array of pixels. In case of CNN, each layer is represented in two dimensions, which makes it easier to match neurons with their corresponding inputs. And okay, so this is an important point. So convolutional layer is a two-dimension array of input neurons or array of neurons, unlike the one-dimension array of neurons that we studied earlier. Now, so all right. So what we actually do is I'll just give you a quick approach, and then we will all right. So I'm going to take this example and try it. Okay. All right. So all right, we'll walk through this example a couple of more times. So feel comfortable to ask questions. So let's say this is our input layer, and this is our convolution layer. This is our input layer, and this is our convolution layer. All right. So what we do is we take a rectangle in the input, or should I take a better example? This is not a great image. Okay. A question from Pratik is, how will it be for audio input? How can we convert it into 2D input? Good question. So let's just deal with audio probably later. Okay. And yes. Okay. So right. So basically, it's you can put it this way that once the convolutional layer started working fine with the images, then the experimentation revealed that the similar thing could be done with the audio. All right. Okay. Yes. In addition to right. So okay. So James' point is that audio spectrograms are often treated as images. All right. This part I wasn't aware of. Good. Good. So let me just give you what's going on. All right. So here, let's say this is our image. Okay. So what we're going to do is we are going to take a rectangle like this and convert that into a single pixel here. The next pixel, okay, similarly, we're going to move this rectangle a tiny bit. Okay, let me try it again if I can try it better. Okay, so let's say this is our input image. Okay, and we're going to create a small rectangle from here to here. Okay, and if I change the color to this one, right? So this is actually all right now. uh, This is better. All right. So for this rectangle, let's say we are just summing up all the, for example, for now, let's say we're just summing up all the pixels and converting it to a single dot. Okay. Then we move this a bit. We move this a bit, and that is generating the next pixel here. Then we move it a bit further, and that generates the next pixel. All right. Similarly, we will keep continuing this way horizontally and fill all the pixels till here. Okay, like this. All right, till till the end. All of this quickly. Okay. All right. Let me just fill it. So this is what happens here. Then we'll take the same rectangle and instead of moving this side, now we'll move to this side a bit. That will generate next pixel here, and then we'll repeat the process of moving in the x-axis. So what we are doing is we are we are moving a rectangle called receptive field, and this receptive field we are converting this whole rectangle into a single value. Okay, this generates this convolutional layer, and then we have second convolutional layer operating on the same principle. All right. So this is a very quick, look into what is going to happen. Did I make sense? So what are we going to do is the input is going to be input layer of 2D, two-dimensional neurons. Okay. What does it mean? The neuron, these are going to be pixels of the image, and we're going to uh, by the way of writing for loops, what we are going to do is we are going to pick up these many pixels first, apply something called a filter to convert this whole rectangle into a single pixel. Okay, then we are going to move it a bit. Okay, then we are going to move it a bit and then generate the second pixel. Then we are going to move it a bit again and generate the third pixel. and so on. We'll continue this exercise. So every rectangle is this receptive field. Every field or every receptive field is going to generate 1 pixel in the first row here, and then we're going to move it a bit to the second, I mean to the towards the height, and then we will again move the rectangle towards and so for every location we will convert this into a pixel. All right, you can. Okay, so you can think of it like we took this image, we maybe applied kind of weights on it, and we converted that by the summing up all the values of pixel into this single. Okay, and so on. So you can think of it this way. So every rectangle, so we are moving this rectangle like a like moving window. We're moving it across our input layer, and and the every rectangle, every position is getting converted into 1 pixel. All right. Now there are many questions at this point. One is, how much do we move this every time? How much do we move these rectangles every time? This rectangle, how much should we move? Should we move this much? Should we move this much? Should we move this much? Second, what happens when you hit the edge? What happens when you hit the edge? Like, should we stop here or should we stop here? Okay, right? Or while we are going from here, okay, and then next question is, what should be the size of this rectangle, right? So what is the size of this rectangle? How much we move? By how many pixels every time do we move? Do we move by 1 pixel at a time? Do we move 10 pixels at a time? Or what should we do in the end? Should we fill it with zeros, or should we just stop here? Okay, should we run it here, or should we just stop here? So those are the questions that we need to answer. All right. So those are basically the hyperparameters, as we usually do. Anything that is looks like indeterministic, we put hyperparameters, and then we do the parameter tuning. All right. So here we'll just take example. Um, so the width and height of this rectangle or the receptive field is basically the two hyperparameters. Then how much we move from here, it's called receptive. How much we move receptive field is called strides. Okay, so there could be horizontal strides. Like if you're moving by 1 pixel, it's called stride in this direction is 1. If we are moving by, say, instead of 1 pixel, we are moving by 3 pixels or 2 pixels, then stride is this movement. So every time the number of steps we take is called a stride. Okay, so 4 parameters, right? First parameter is the width of the rectangle, height of the rectangle. The stride, how many steps do we move this every time? Okay, because there'll be chain of overlapping rectangles, right? Okay, so how do we move this? And should we move it 1 pixel at a time or 2 pixel at a time? And that is decided by strides. So 4 parameters, right? Then next hyperparameter is that how how do we uh, handle the edge case? As in, if we are having, do we do this? As in, do we let this receptive field go out, or do we stop here? Okay, or you can say, do we stop here, or do we stop here? So this is again hyperparameter, do we fill it with null values, or do we stop at the edge? Okay, so that's an important bit. Now, moving ahead, we're going to go back, uh, go back to this example again. A question from Binta is, how does rectangle move? How to control its direction? We basically move in the rows and columns. All right. How does it change to the next column? Good question. So what we do is, the way we run the for loop, for I is less than number of rows, and then in the loop we say for j equals to 0, right? So first I will remain 0, and then for each of the rows we move the rectangle to the end, then that will finish there, and then the next row will start, and the same process will repeat. Okay, so how do we generally move in the matrix? We generally write a for loop, correct? So we generally write a for loop. So we generally write a for loop like I equals 0 and I less than the width of image and I plus plus. This is how we used to write, right? And in case of Python, we do a similar thing. Okay, we do a range instead of this. So you can think of it this way: for I in range of, what was that? Width. Okay. And then we have for j in the range of height. So for each row in the actually it has to be written either way is fine. For each height, right, this is how we do programmatically, right? Is that your question? Okay, and then we choose the rectangle accordingly. So our rectangle equals I, the rectangle, if the rectangle is defined by the left top corner, so it'll be I comma j and I plus width of the rectangle, and -1 actually. Okay, and j plus height of the rectangle -1. -1 is we call for the edge cases. Okay, so this is how we generally define our pick the rectangle, right? And then our pixel value at every point is going to be some filter, okay, some filter on this rectangle. We will call that filter. Converting this rectangle into a single pixel is done via a mechanism called a filter. We apply the weights on this image and we get this. So that's called the filter. All right. Great set of questions. Keep the questions coming because this is a very important subject, and most likely the same question everybody would have. So please feel free to stop and ask the question. Okay. Now there is an idea called zero padding. Since we are moving this rectangle in the input layer, we would hit the edge. So if the zero padding is enabled, it will fill the edges with the zeros so that when the rectangle reaches here, these values in the input image are considered as 0. Okay, so this input field, or our rectangle, the one that we were moving around, so this one is basically overflowing, going over the edge. If your image was still here, the white one, let's say this was your image, and we were moving the rectangle around it in a rectilinear motion. So we basically would, when we go to the edge, it will overflow, right? So When we enable the zero padding, enabling zero padding or not enabling zero padding is a choice. When we enable zero padding, we would get the, we will basically let the rectangle go out of the picture until the point at least one of the pixels is in the rectangle. Okay, so what I mean is that when we are moving this rectangle around, right, we will letting it go till here, let's say the last pixel, okay, is basically in this case what will happen is here where there is no image on which this rectangle has to be applied is called the is filled with zeros. This part where it is going beyond the boundary is filled with the zeros, or you can think of it this way as well. Let's say this way. Okay, so here only one pixel is true while the remaining is empty. Okay, so this is called zero padding. We fill this part with zeros. Okay, we fill this part with zeros and let it process. All right, so this is essentially what we call it as zero padding. So we let it overflow in all directions and fill the remaining rectangle with zeros and project the value or compute the value in the next layer. Okay, so the number of neurons in the next layer is a function of what all? Anybody? A question from Pratik is zero padding only a single pixel around? No, it could go more. Okay, it could go more. Right. So it's a function of how big a stride you have. Okay, let's say we are taking 3 steps at a time. So let's say we are here, and when we take the 3 steps around, it goes here. Okay, that means we are going to have 3 pixels out of the picture. So we'll be filling the 3 pixels with the zeros. Okay, so generally the number of pixels that are filled in is based on how big a stride we have. If we are only moving 1 pixel at a time, then the moment we hit here, we basically have overflown, and this is where we will stop, and by filling the one that is overflowing with zeros. Okay, now question to all of you is how big this output layer are going to be, or convolutional layer, which is the result of the input image, is going to be. Okay, okay, so let me ask this question again. Imagine that we have what all it is a function of. Okay, how many pixels are there in this layer? What does it depend upon? What does it depend upon? How many pixels are there in this layer? What does it depend upon? Yeah, or is it fixed? Question from answer from Pratik is the size of the smaller rectangle. Okay, this one. Okay, and the movement around X and Y, how much it is moving, as in how many steps it is taking, the stride, how many what is the stride? Okay, in horizontal as well as vertical, the size, and okay, good, keep going. So how many pixels are going to be in this layer, in this layer? What is the size of this layer? Is Yeah, so on what, which all parameters does this size of this layer depend upon? So right, the answer from Pratik is the size of the rectangle, right? Then the movement of x and y, yes, how much the stride, how much we are moving in one go, okay? And the size of padding, yes, whether we are allowing the padding or not, whether we are allowing the padding or not, and okay, and yes, yes, and the size of input image also, right? The size of input image. So the number of neurons in the next layer is a function of size of input image, size of the rectangle, right? And the stride, as in how many are we moving in a single go, right? Yes. So how fast the rectangle move in one epoch? So sorry, we basically we the objective is to basically move it, right? Move it as fast as possible and compute the next layer. Question is, how many pixels does it move in a single go, right? Does it move once or does it move like this, right? This, then jump to the next, then jump to the next, and jump to the next, right? That's called stride. Okay, great. Great set of answers. So please feel free to stop and ask in case anything is sounding confusing at this point. Okay, so so the neuron, now let's just get a bit mathematical. So neuron in the row I and j of a given layer is connected to the outputs of the neuron in the previous layer. So neuron in this layer is connected to the previous rectangle, right? So the rows at, if these were the rows, right? These were the rows and these were the columns, okay? If these were the rows and these were the columns, so let's say this is ith row, this is ith row, it is starting from ith row here. We are saying the height of the rectangle plus height of the rectangle, right? And if this is j, this is the width of the rectangle, right? So and so on. Okay, so that's what we also did here, that that the rectangle was defined like this. Okay, the rectangle was defined like this. So for I in the range of height, for each height and width, not weight, it is supposed to be width. Okay, for each height and width, we are going over 1 pixel at a time and we are computing the rectangle, right? Here, here, since we are going 1 pixel at a time here, the stride is 1, we could actually have moved, say, n pixels at a time, right? In that case, we'll have to multiply by the stride. Okay. Okay. So yeah, this diagram is clear. Okay. So in order for the layer to have the same height and width as the previous layer, it is common to add zeros around the input, as shown in the diagram. A question from Binta is how fast the question from Binta is, does -1 refer to overlap? No. So overlapping is completely okay. Overlapping is just another rectangle. We compute it again and give the value. Okay. So we let it overlap. Say this one, right? Let's say this is one rectangle. We compute its value, generate this. Then we move to the next. We move this rectangle a bit, compute the next pixel. Okay. So all we are doing is moving the rectangle around, taking the photo of it and keeping it aside. All right, that's what we are doing. Taking a photo means just converting that into a single pixel and then moving ahead. Okay. A question from Binta is that why do we have -1 while we are computing this, right? This -1. Because if you see, let's say the width, let's say this one, right? Uh, okay, let's say this is our 0th row, or let's say this is our 0th row. Okay, this is our 0th row. Okay, and we are saying, okay, okay. Imagine that this was, let's say, 0. This was no, actually, should I start from maybe this side? Okay, let's say rows are varying from this to this, columns are varying from this to this. So our row is starting at this point, correct? Our row is starting at this point from here, and it's going till here. So if the okay, so if row is 0 plus 3, so this is going to be 3. So this is, okay, let me again say, if this is 0, 0, 1, 2, and 3, right? If we just add 3 to 0, the index, the end index is going to be 3, which is 4, which is going beyond the rectangle, right? So this is, if we say our window size is 3, right? 0 plus 3 is going to be this, the 4th row. Therefore, we are saying I to I plus fh minus 1, because indexes are 1 less than, indexes are starting from 0, correct? Because the last pixel I plus fh is not actually included in this rectangle, right? The -1 refers to that, right? So if we have, say, numbers from 0, 1, 2, and we say that give me consecutive 2 numbers. So what you'll do is take an index, add 2 to it, and give me from ith to I plus n minus 1. All right? Right? Or let me just draw it probably. Let's say here, let's say here, we have numbers from, okay, 0, 1, 2, 3, 4, 5. Yes. So if we say, give me 2 numbers, or give me 3 numbers, starting at the index 3. So we'll start here, we'll add 3 to it, right? That'll become 6, correct? But these are the 3 numbers. Starting at 3, give me 3 numbers. So it's going to be 3 to 5. 3 plus 3 minus 1, not 6, correct? That's the reason. That's why you see -1 here. All right? Did I make sense? Should I repeat? So if I ask you, give me rows of width 3, starting at row 3. So 3 plus 3 is 6, right? So 6 minus 1 is 5. So we say I plus 3 minus 1. So 3 to 5. Okay, this is I equals to 3, and this is I equals to 6. If we say I plus, give me 3 starting from here, and we give, okay, so this is a I, and this is a I plus fh minus 1, right? So if fh is 3, this is what we are looking for. All right, all right. So basically, that's why we are subtracting 1 from it. Great, great. Yes, that means we are including the starting point. So we both are included. So we are saying rows starting with I up to and including this row. Okay. Similarly, column starting with J up to and this point. So this rectangle whose left coordinate is I, and so whose so the left, so the rows are this and up, starting with this and up to this, including this, and columns starting with this and up to this. So I and I plus fh, I and I plus fh minus 1. Okay, and j and j plus fw minus 1. Okay, so that's how we are doing the calculation. All right, so we are basically going to move this rectangle around over the input layer and generate the next layer. Okay, so now it is possible to connect a larger input layer to a much smaller layer by spacing out the receptive fields, right? If we are moving this, we are jumping this one a lot, the outcome is going to be very smaller, right? So the distance between two consecutive receptive fields is called a stride. There could be horizontal stride as well as the vertical stride. So while moving from one row to another, we use SH. While moving the one column to another, we use SW as a step size. Okay, so the stride is also called step size, and in this, when we are moving the receptive fields. All right. All right. So this diagram shows how it is being computed. So this is how we are moving the receptive fields. Here, what's the stride size? Anybody? The horizontal and vertical in this particular image? One, right? And does it have padding or not? It looks like it has padding. Okay. And what's the size of the rectangle? The receptive field is 3. Correct. All right. I hope this diagram is clear to everyone. So we are converting an input image to something else by applying some kind of filter on this receptive field that converts a set of pixels into a single image, into a single pixel value, not single image. So this 3 by 3 rectangle is getting converted into a single pixel. Okay, so in this diagram, a 5 by 7 input layer plus 0 padding is connected to 3 by 4 layer using 3 by 3 receptive field and a stride of 2. In this example, the stride is the same input direction, but it doesn't have to be. Okay, so you can see it clearly. So in this diagram, we have 5 by 7 input layer plus 0 padding is connected to 3 by 4 layers using 3 by 3 receptive fields and a stride of 2. In this example, the stride is the same in both directions, and it doesn't need to be in that same thing. All right. So again, if we have taken sh number of strides, so the 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 row I and j in the output column, the upper layer, is connected to the outputs of the neurons in the previous layer, located at I into sh plus from so the outcome here is a function of how many strides we have taken, right? So this is how it is going to be. So the output in ij is a function of I into sh, right? So this this one has been achieved by this rectangle. And how do we find out which rectangle is the input layer is? By multiplying this I with sh, the number of horizontal strides, that's the beginning of the rectangle, till the width of the receptive fields. Similarly, number of the beginning of the rectangle is determined by number of strides we have taken, right? So first will be the first one here, the second will be like this, and third. So every time if we are jumping by 3 pixels, so the here we have jumped by, say, 3 into 3, while we'll reach here at 3. Okay. So for this one, let's say we use the first rectangle, right? And we are taking a stride of, say, 3. We are jumping by 3. So this one will be after 3 pixels. This one will be again after 3 pixels. Then this one will be again after 3 pixels. Correct? So that's why we are multiplying. We're multiplying I and j with sh and sw. Okay, to find out which rectangle it is. Okay, is it clear? This why the row I and j maps to a rectangle that's starting from I into sh and j into sw. If you just think about the beginning, the left top corner, the left top corner of this rectangle, right? Here. So this one, right? So left top of this one is going to jump by a number of strides. Okay, so the left top is basically a multiple of SW and SH. Okay, so given I and J in the output layer, if we have to find out which rectangle this one corresponds to, then we can use this kind of a formula. We can say I multiplied by SH and J multiplied by SW. Okay. All right, is it clear? Should I explain again? Okay, so let me see if I could. Okay, imagine that we had a rectangle like this and a rectangle like this. Okay, and let's say there are only two. Okay, and we have, let's say, another rectangle. Okay, like this. Okay, this is our receptive field. All right, now this one has, say, can I draw it in some way a little bit more easy? 1, 2, 3, 4, 5, and 6. Okay, and let's say this one is covering 3 of these. Okay, I'm just hoping that. Okay, let me just try it. Okay, so let's say this is our input image, which has so many pixels. It has how many? 1, 2, 3, 4, 5, 6. So this has 6 pixels this side. Okay, and this one has how many pixels? 1, 2, 3, 4, 4 pixels. Okay, and this one is having, say, this width. The width of this one is how much? 3 by 2. This one is having the width of 3 by 2. Correct? So, and let's say we start from here. Okay, so this one, let's say this is called 0 and 0. This one and this one is called, say, 1 comma 1. Okay, this is 0 comma 1. Okay, now the rectangle that, oh, where did my rectangle go? Yeah. Okay, so this rectangle that you see here is the receptive field. So we put it here, and then let's say we jump by 3. We're jumping by 3. Okay, and then we again jump by 3 vertically, and then we jump by 3 horizontally. Okay, so what we see here is that the I and j, 0 and 0, is this one is belonging to this region, right? And if we have taken, say, only one stride, we are going to we're going to add it with with the with those many strides. So here, this one is a result of how many times did we move the rectangle, meaning how many steps we had. If we are moving, if let's say, let me ask you this. So moving to I equals 3 would involve how many jumps? How many jumps? Let's say we were moving this to 1, 2, and 3. How many jumps it will involve? It'll involve the movement how many times? 3, right? That means how many rectangles we had moved by then? How many rectangles did we move by then? 3, 3 strides, right? 3 strides into stride size, correct? That's fine. All right. So, and every time we move, okay, so I should have drawn one more here, just that it's going to be a little harder one. Okay, let me just keep it aside. And if I just, can I just copy all of these? Okay, so yeah, let's not worry about it. So I think you got the idea. So moving to I equals to 3 from I equals to 0 would involve 3 jumps, right? 3 jumps means 3 strides, and therefore each stride is of some size, and therefore let's say stride is of size say 2. So that will lead to 9 values, ninth value in the input. Okay. All right. So that's what is happening here. So why on every stride we are moving here by 1, while we are moving by here by stride size. So here the ith column, ith row means I into sh. Okay. While here we are moving by 1, here we are moving by stride size. Okay. Therefore, for I and j, to find the left top corner in the receptive field, if we want to find out the left top corner of the receptive field, what we do is we just multiply I and j with the width and the height. Okay. So we're basically moving this rectangle by the stride size. All right. Did I make it clear or confused you? So while on the outcome layer here, we're moving by 1. Here we are moving by the stride size. Okay. So at any point I and j, at any point I and j, if we have moved, let's say here 3, that means we have moved here 3 strides, right? So left top corner of the receptive fields, left top corner of the receptive field is going to be 3 into the stride size. Okay. Okay. Here the stride size is W, right? So I into the stride height. We are not multiplying the, okay. So stride size as in uh, every step size in I or J. Okay. So okay, let me ask you this. If we are moving from here till here we are just moving by 1, correct? We are moving by 1. So here we are moved by 3. Okay. So okay, let me try to, actually the I and J I have not marked correctly. So stride is horizontal as well vertical, either horizontal or vertical. Both, it has both the ways. Okay. So when we are computing J, we use the vertical stride. If we are computing the I as in the rows, then we are multiplying using the horizontal stride. Okay. So let me just put it this way. Okay. If, let me just walk you through this. Okay. And no, stride is basically two values, one for moving in horizontal direction, other is moving in the vertical direction. We move either horizontally or vertically once, right? We only take one step at a time. We don't just move in both directions at the same time. That way we will miss some of the rectangles. Okay. So yeah, let me explain again. So okay, let's say this is our I. This way our I is moving. So this way our I is moving, this way our J is moving. This is I and J. Okay, this is I, and this is the way we are moving the J. Okay, so here I and J are 0. So when we are moving this by 1, here the receptive field, will move by 3, correct? Since our stride size in both the directions, here this is 2, vertical direction, the stride size is 2. Here, the stride size is say 3. Okay, let's just take an assumption. So horizontal stride, we call the horizontal stride equals 3, 2. So actually the coordinates in this are kind of messed up. The way we always do the arrays is this way only. Okay, so here I and j, uh, so for each I, let's say we moved by this. So we are basically multiplying by the height of the vertical stride. So I think we'll have to just change our coordinate system a bit. Let's say, right, this is how it is. So our I is increasing in this direction for some reason, and so on. So essentially the idea is very simple, that for every coordinate here, when we move by 1, here we are moving by number of strides. So here the I is changing from 0 to 1. So let's say I is 1. So I 1 multiplied by 3, that will be the coordinate of this location. And then this will be the third coordinate, right? 3 here. And then if there is another one here, the image was bigger. So again, this will basically move by 3. So if we multiply the I with 3, we will get the coordinate of the left top corner here. Okay, this one. Similarly, if we multiply j with the vertical stride, we will get the coordinate there. All right, so that's the sole idea. All right, I hope you got the picture. So the row I and j in the upper layer is connected to the outputs of the neurons in the previous layer, located at this left corner and this top corner. Okay, I into sh and j into sw. Okay, so we have reached I in the upper corner by moving these many times. These many times. And how much did we move every time? By sh. Okay. Similarly, on the vertical side, this much we have moved, these many times we have moved, and how much each time? This much. Therefore, in the input layer, the rectangle or the receptive field is located at this corner, this point. Okay. All right. So here this is again, it is going to be JS2. This is, yeah, it is going to be like this. All right, let me just correct it. Yeah. So basically, this is how it is going to be. All right. I hope this is clear to everybody. There's no doubt, right? All right. Now, so what we learned was that we move the receptive field and compute something such that we get a singular value out of the whole receptive field, right? Out of the receptive field, we compute a single value. That's what we have learned, but we don't know how. Okay, this is done by the way of something called filters. We apply filter on every field. We apply we apply the filter on every receptive field to convert that to a single value. Okay, there could be many filters, there could be many kinds of filters, and every now and then people keep on coming up with different sort of filters. Okay, and we learn that so essentially the filter weights are something that we learn as part of the process of machine learning. So we start with a certain filter, and then we learn the various parameters of the filter, as in while we build the network using backpropagation, the various values of filters are computed. All right, so let's take a look at this. A neuron's weight can be represented as small image, the size of the receptive field. The neuron's weight can be represented as a small image, the size of the receptive field, right? And this is the below two conversions. So what we did here was, this is the, you see, there is a tiny bit of image here. What we have done is we have taken this as a filter, applied it on every receptive field. We took this filter, kept on applying it again and again, again and again here. While this filter, when we applied it again and again on every portion by moving, say, 1 pixel at a time, using a stride size of 1, we got this. While we got this in case of this vertical filter. All right. So what we see here is these are the two filters, right? And let's take a look at what does these filters have. Imagine the vertical filter looks like this. Okay. The vertical filter has this filter, right? This filter looks like this, and our input image looks like this. So what we are doing is we are applying this vertical filter on this image. So first of all, we're going to apply this on, say, this rectangle, right? So zeros multiplied by all of these zeros is 0. So this one multiplied by this one multiplied by this. So you can see the colors are basically for each individual like correspondence here. Okay, that's a right. So this way you can clearly see that which one is being multiplied with which one. So the result is these all will become 0, this all will become 0, and these all will be 30, 10 plus 10 plus 10. The resultant is kept here. Okay. So it looks like a vertical filter because it's leaving a vertical strip here. Okay. So it has a vertical strip as in 1, 1, 1. Had it been all of them 0 except for this horizontal line, we could have called it horizontal filter. Okay. A question from Binta is, if we set up a Cartesian coordinate system is I and j is equivalent to x and y, that's right. Okay. So yes. All right. So is this clear to everyone? So let's say this is our receptive field. Okay. This is our receptive field and this is our filter. So for each receptive field, we're converting them into a single pixel. How? By applying this filter. How do we apply this filter? This filter is just some random permutation, or we'll see to that there are many creative ways. So here, these zeros are being multiplied with this. So color corresponds to who multiplied with who. So this multiplies with this multiplies with this multiplies with this, and these multiply with these three, and so on. So the resultant is how much? 30, right? And this one, do you think this is correct? So then when we multiply this with zeros and this, okay, again we move it further. So this time the value is 0. Okay, this time the value is 0. Okay, so this is actually like taking taking a uh, taking black paper, cutting a vertical slit on it, and moving that on this image, seeing this image through this one. Okay, through this one. So if it has vertical lines, it will have uh, like more values. If I had like horizontal line mostly, then it will have lesser values. So vertical lines is give a basically just like you think of polarization. When you look through the, you can't see the horizontal lines clearly. So here, since the data is vertical lines, therefore therefore it'll get more emphasis. All right. Similarly, we keep on moving this receptive field like this. Okay, and we continue to fill the entire one here. Okay, so we continue to move it entirely. Okay, in the same way we apply the second filter, say horizontal filter, to compute the output. So the first one is a this one is a black square with the vertical white in the middle, which is essentially, here it is 7 by 7. In the example, for simplicity, we have taken 3 by 3. Okay, so it's a 7 by 7 matrix full of zeros except for the central column. In our example, it's 3 by 3 just for the example. Okay, just so that it's very clear. The neurons using these weights will ignore everything in their receptive field except for the central vertical line. Okay, since all the inputs will get multiplied by zeros except for the ones that are located in the central vertical line. All right, that we just saw. The second filter, is with the horizontal white line in the middle. Okay, so we can actually clone this and just experiment with a bit about, say, let me just go back here, right? This one. Okay, let me just put it here. Okay. The second filter, let's say second filter is horizontal filter, which has these ones. Okay. All right. Or should I just copy the second values? Okay. Let me just take this example. This looks better. And all right. Imagine that it was a 1. This was 1. This was 0. This one 0. So how much this value will be? Yes. Still 30. Okay. And yeah, great. So basically, this will be applied in the same fashion as we have shown earlier, and this will compute the next output layer. All right. So the second filter is a black square with a horizontal white line in the middle. Once again, the neurons with these weights will ignore everything in their receptive field except for the central horizontal line. Okay, so now let me just do an experiment with this. So if let's say all of these values were basically 0, okay, how do I quickly make them 0? Okay, let's say this. So it's a vertical kind of image. Okay, and say this. Right? So when we basically are computing this one, it is going to give us 10 here, right? And then we move to next one, it's going to give us 10 again, right? And so it basically, the vertical strips, instead of being 30, it has resulted in 10. So when we are applying a vertical horizontal filter. This is horizontal filter. Okay, and when we are applying the horizontal filter, the basically it won't give us this kind of values. I'm sorry, it won't give us 30 30 30. Instead it is going to give us the uh, it is going to give us the 10 10 10. So you can see that if the image is vertical and is more focused to the vertical, then we are getting less by applying horizontal filter, the image is dimming at the end. If we are applying say vertical filter on this, here we will get say here we might get zero, and but here or here when we are applying, yeah, when we are applying the vertical filter here, we might get 30. When we are applying the vertical filter here, we might get 30, while rest of it will become zero. So so it's exactly the same effect as we move the vertical or horizontal slit, or when we try to see things through a horizontal or vertical slit. Okay, so so it's basically trying to emphasize on the vertical line and horizontal lines. Okay, so these are two examples of the filter, and these filters are what we use in order to generate the next layer. And the various values or various weights of the filters are learned as part of the backpropagation. Okay, so this we have already talked about. Now, up to now, for simplicity, we have represented each convolutional layer as a 2D layer. Okay, as a 2D layer, but in reality, it is composed of several feature maps of equal sizes, so it is more accurately represented as a 3D. Okay, imagine, so in reality what happens is, when we are inputting an image, input image could have multiple colors, right? As well as when we are applying multiple filters, we will get the multiple feature maps. Okay, so so let's say we are applying the horizontal filter, we will get one set of output the way we got here. We got one set of output when we apply the vertical filter. When we apply the horizontal filter, we got another set of output. So these outputs are stacked together to form a 3D convolutional layer. So the convolutional layer is actually a 3D layer, and these sublayers are the result of applying one filter on the receptive field at a time. All right. Also notice that the input image that we are talking about, the input image could be could be could be of multiple layers. Imagine, look at this image, for example. When we look at an image normally, it's a 2D image, right? It's a 2D image. But every pixel has three values: how much is red, how much is green, and how much is blue. That's the color of the image. Okay, so the color of the image is actually the three dimension in itself. Okay, so so basically the image therefore is basically having multiple layers. Okay, so first layer representing how much is red, second representing how much is green, and third representing the how much is the how much is blue. Okay, so an individual pixel value represents the actual value of the color. Okay, whether it's 100% red, in that case it'll be 255, otherwise it'll be some between value. So an input image, when we think about input image, is having uh, 2xyz direction, 2xy, so two dimensions for representing image coordinates, and third dimension representing the channels, Okay. Now, within one feature map, all the neurons share the same parameter weights. So when we are applying a filter, we apply this filter on all of these layers. Okay. So when we applying, say, horizontal map, we're going to apply on all of the layers, one layer at a time. Okay. So the whole cube, it's not the rectangle that gets translated into a single point, it's the whole cube that gets translated into a single point. Okay. So earlier when we were we were discussing this part, we were converting a two-dimensional object into a single value, right? Into a single value by applying the filter. In fact, when we are applying the filter, that filter first is applied to red, then applied to green, then applied to blue, right? And the resultant value is combined together to give the value of the pixel in one of the layers. So let's say this is a vertical slit, so horizontal slit will be applied to red, green, and blue. And then the resultant will be combined to form a single pixel. Then we'll move by stride to the next receptive field and do the same thing. We'll do the same thing just like this again at this point. Similarly, for the second layer, we will again take the filter for the second layer. Okay, so for the first, let's say we had multiple filters. So each filter will apply on the whole cube at a time and give us one layer here. So one filter results in one output layer, though one filter applies to all three input layers. Is it clear? So a filter is applied to all the input layers and generates a single layer. Okay. We also call it feature maps. These are called feature maps. So each convolutional layer is composed of these filter maps generated by each of the filters. All right. Does it make sense to you? So we are just moving one step in this, instead of applying the filter, on only on horizontal, we apply this filter on all of the layers. Okay, we had one nice diagram at this point. Okay, I'll come back to that again. Okay. So a question from Binta is, how many filters are there in each convolutional layer? We can apply as many as we want, right? As many as we want. So here, the more the number of filters you apply, the more will be the number of sublayers in this particular layer, in a particular layer. Okay, if we apply 10 different filters, horizontal, vertical, slanting, left slanting, and so on, or a circular, we would get so many of these convolutional layers. Okay, so many of these layers and so on. All right. So let's take a break for 10 minutes and we will be back after 10 minutes. A question from Pavan is, backpropagation is here to adjust weights. That's right. The weights of each filter will be adjusted by backpropagation. We really don't know that when we are applying a filter, we are just applying the weights of that filter, right? So we have to find those weights eventually by the way of various permutations, or you can say by the way of using backpropagation. And that's what we are going to do. All right. So towards the end, what we are going to do is we are going to say here we observe that okay, how much is the error in this layer, and accordingly we adjust the previous weights. Okay, based on the rate of change. All right. So what we learned so far was here every we call that feature map. These are called feature maps. These are sublayers of the convolutional layer. So convolutional layer is basically composed of each individual pixels, which are the resultant of applying a particular filter on the input layer. So when a filter is applied, it is applied on all the layers of the input layer, but it generates only one layer. Okay. So each filter generates one layer. Okay. So, but here, so within one feature map, all the neurons share the same weights and biases. What does it mean? Meaning, a filter is applied a same one filter means set of weights and bias term. Okay, so we are going to apply here when we are multiplying, like the way we talked about the applying the slate, it was nothing but the weights, right? So those weights are going to be applied on say first layer, second layer, third layer, and whatever is the resultant we get here. So one feature map, and the same weights are going to be applied everywhere. Okay, the same weights are going to be applied everywhere on all of the receptive fields. The filter does not change. The weights does not change for all the receptive fields in an input layer. Okay, so all right, so but different feature maps may have different parameters. Okay, so a neuron's receptive field is same as before, but it extends all of the previous layers. So when when we think about the the eye looking at a particular rectangle in the photo, it's looking at all of its colors, right? Therefore, the receptive field is not only a two-dimensional thing, it is a three-dimensional, or it's a in our case, two-dimensional plus a color. So, so when we are applying a filter, we apply to all the layers in the input the same filter uh, all over. So in short, a convolutional layer simultaneously applies multiple filters to its input. So we have one filter. We happily apply that filter all across the channels and all across the rectangles, all across the various receptive fields, and we generate one feature map or one sublayer of the convolutional layer. Then we pick another set of weights and biases, or we call that filter. Filter is nothing but bunch of weights and bias, bunch of weights and a bias term. So that one we basically apply again here, and then on all of the channels as well as on all of the receptive fields on all of those rectangles, the one that we moved, and that will generate another feature map. This way, the number of feature maps are a function of number of input filters that we decide upon. Okay, and no matter how many layers are there in the input channel, we get only one output layer, one layer if we have only one filter. Okay, so in short, in short, a convolutional layer simultaneously applies multiple filters to its input. And also please note that while we are doing this computation, instead of only applying one filter at a time, we apply multiple filters. Basically, we generate all these layers simultaneously. Okay, so we generate all these layers simultaneously. For simplicity, we can always think that this map is generated once, then this one is generated, then this was generated, and so on. These feature maps. Okay, but in reality, what we do is we take all these multiple filters and pick a receptive field here, apply those multiple filters, and generate the feature map simultaneously. Okay. Now, the fact that all neurons in a feature map share the same parameters dramatically reduces the number of parameters in the model, right? Since the filter, or you can say the set of parameters, are small, and those are the same parameters that are applied to all the receptive fields in the input layer. Therefore, the total number of parameters are a function of how big is the filter that we are applying, multiplied by how many such filters do we have. So this will dramatically reduce the number of filters. In our case, if we take a look at this example, how many values are there in the filter? 9, right? 3 into 3. And how many such filters are there? 2 such filters we applied, correct? So therefore, there are only 18 values, 18 weights that we'll have to find out as part of learning. So the fact that all neurons in the feature map share the same parameters dramatically reduces the number of parameters in the model. All right. So it means that once CNN has trained to recognize the pattern in one location, okay. Now, if we have trained this model to recognize the pattern in one location, it can recognize the pattern in every dimension. Let me just turn off my phone. Okay. And so one more very important part of it is that since we are applying the same filter here as well as here, so we are going to get the same result at the end of it, right? So imagine that we have, let's say, face of somebody here. Let's say we have face of somebody here, and we applied the filter to convert that into a single pixel. Now let's say here, the result is face found. This is true. Face not found, this is false, correct? Now imagine that we move the face to this side, okay? Again, it's going to be saying that, okay, face found here, but not here. And the resultant is again the same. Okay, let me try to show you this part. So this is again a very important property, and I mean, this is basically the intuition around the two-dimensional objects as opposed to the single-dimension objects. The reason why we use this is exactly the reason why we use CNN over the fully connected one. Imagine that our object earlier was, let's say, here, okay? And we have this filter, which is basically saying yes, yes, if the object is found in this rectangle, and no, if the object is not found in this rectangle, right? In the next layer, we are just saying or. Okay, let's say here, this is or, and so the object is found because object was found in the first rectangle. So first filter is just detecting an object. So since it's the same filter here and here, it detects the object in this one, but not in this one, right? But this filter is being applied on both the values, and therefore it says, yes, the object has been found.
correct? Now, if the object moves from, if there was another picture in which object was not here, instead object was in this another receptive field, correct? And since we are applying the same filter, this time, this will say 1 and this will say 0, okay? This filter, when it is applied, it says, okay, 1, this is found. Now, the resultant of these is still the same. So, the point that we are trying to make is that even if things move in the rectilinear direction x and y way, the resultant is going to be the same. Okay, so that's one of the reasons. If because in the case, had this been a single direction or one-dimensional array of pixels, moving the rectangle from here to here will have dramatically different impacts. It'll be completely different set of pixels, and with the neural net will have not much of correlation between the two. All right. So this is why this two-dimensional way of doing things or three-dimensional way of doing things works out, specifically in the cases of two-dimensional or three-dimensional objects. Okay. So is this example clear? Balaji, Gigi, James, Shahrukh, Pavan, Pratik, Ross, and Shiva. No? Okay. So since it's the same filter applied on all the receptive fields, therefore moving the object is going to have the same impact. And hence CNN is tolerant of objects moving, and sometimes even object is skewing to either direction and so on. Okay. All right. So basically, in contrast, once a regular DNN has recognized a pattern in one location, it can only recognize pattern in that location if we are moving, say, an object by a couple of pixels, that will actually offset all of it. It won't be so predictable in the outcome. So input images are also composed of multiple layers, one per color channel, that what we discussed. So the input layer also has multiple layers, and there are typically, say, red, green, and blue. If we have just black and white images, there will be only one channel, that how much brightness is there. And sometimes some of the images are far more rich. Like, for example, the satellite images capture extra frequencies such as infrared frequencies of the light, right? How much heat was there at every pixel. So there are all kinds of images, and the input layer could be really, really complex in some of the cases. All right. So specifically a neuron, this one we have already discussed. Okay. So when we are a neuron located at I and j column of a feature map K in a given layer L is connected to the outputs of neurons in previous layer located in this particular location, meaning those many strides we have moved. Okay, those many times we have moved. It's the ith time the stride in the vertical way, and jth time in the horizontal way across all the layers. So here, please notice that for any feature, a single feature map is bound to all feature maps in the previous layer. This feature map is generated by combining the features of all the sublayers of the input layer. Okay, that's what it is trying to show. Okay, this we have already understood that all the values in receptive fields are combined at a particular location to give INJ's data. Here, there is one more thing, that all of the feature maps, meaning all of these, the color in the red, color in the green, the receptive field in the red, receptive field in the green, receptive field in the blue, all of these are combined to give you a singular value. Okay, so that's the important part. Now, again, note that all the neurons located at location I and J column, here I and J column, but in different feature maps are connected to the output of exact same neurons in the previous layer. So a filter is applied on multiple input layers, all of the input layers in a single shot, all of the sublayers of the input layers in the single shot. So that's what is done. All right. This is going to look really mathematical. Don't worry, it's not that difficult. It's just 3 for loops. Okay, just 3 for loops. We are going over all of the rectangles, all of the pixels, and then all of the layers in the previous one, and computing the resultant pixel. Okay, that's what we are going to show you. So let's say this is our, this time, let's say we are talking about second layer. Okay, so let's call it ZIJK. K is the number of layers. I is the I and J is X and Y. Okay, now let's call it ZIJK. Now we have, as we have explained earlier, SH and SW are the vertical and horizontal strides, and FH and FW are the heights and width of receptive fields. And Fn dash is the number of feature maps in the input layer. This is Fn dash. Okay. So Zij represents each of the neurons in the output layer. Fh is the width of the receptive field, this width, and Fw this height, and Fw is this. Okay. Stride is how many times we are going to jump it while moving around. Okay. By how many pixels are we going to jump? That's stride. Now, xi dash j dash k dash is the neuron located in the previous layer. This is the one we are talking about, the current layer, ijk. This is the previous layer. And I dash j dash k dash is the output of neuron located in the previous layer at some I dash j dash, and k dash is the feature map here. Okay, feature map here. Now, bk is the bias term for the feature map k in the layer. Okay, so for the whole layer, or all of the layers in a while we are generating this, there is only a single bias term. Single bias term. Bias term is 1 per feature map. Okay, for this whole one, there is only one single constant called bk. Okay, you can think of knob that tweaks the overall brightness of the feature of map k. Question from Binta is, does stride means moving the steps, right? That's right. Okay. Stride is the width of your step. Okay. Striding means jumping around. All right. Now, there is something called connection weights. WU, WK, there's a connection weight between any neurons of feature map K of the layer 1 and its output at this. Okay. So this W is nothing but the filters, the weights, the filter, the way we had 0, 0, 0, 1, 1, 1, and 0, 0, 0, right? This one is that those weights. Okay. So this one is a connection weight between any neuron in the previous layer, in the feature map layer here, of layer, and the input located in row U, V, and feature map K. All right. So that's what it is. So this is how it looks like. So all we do is we multiply. What we do is for every for the whole window of receptive field, that's for all the heights, for all the widths, and for all of the input layers, these are all of the input layers, what we do is we multiply the previous pixel uh, density, or we multiply the neuron value in the previous layer with something called this weight. This weight is not varying with u with it's only varying with u and v, right? Meaning it's varying only for the filter size. It's and right, and it's a function of the 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 whole filter. Okay, so that's what is going on. And so essentially what we do is we apply this complex thing is nothing but we are taking a rectangle that contains these weights, the small rectangle that contains weights. We apply that weights on this, and we move that weights around. That's what we are doing. So that's what the way we demonstrated to you earlier, like here, you can see. So when we look at the filter now, filter is kind of composed of three layers itself, and we are applying this filter. We are applying this filter on every section. So what we are doing is for every layer, right? The first layer, red layer, green layer, and blue layer, we are applying the filter here, filter here, filter here. How? By multiplying these values, by multiplying this with this, this with this with this, and so on. So, and then summing up all the values, and then summing up again, okay? And then we are adding a bias term. Then we are adding a bias term. Okay, and that's how we are computing the output value. Okay, so this animation could give you a better example. So it's nothing but we are looping over all the layers, right? All the layers. This is the first loop here is basically saying sigma over k dash, meaning fn dash, meaning do it for all over the layers. Okay, of the previous one. Then for every location of the window, for every u starting from 0 till the height and the width and so on. So this is what's going on. For every this is happening for each of the pixel in the output. This is happening in for each of the pixel in the output. So all right. A question from Bintao is that does IJK follow permutations or combination? So you can see this. So this is I, J, and K. Okay, this is I, J, and K. K right now is fixed. We are saying only we are applying one. This is a one composite big filter. Okay, we are applying only that. Okay. All right. So you can see that this value, let me just go back to the previous one. This value is being calculated from this rectangle in first layer, this rectangle in second layer, and this rectangle in third layer. Okay, and how? By applying a kernel filter, we call that kernel or weights or filter. All the three things are used interchangeably: kernel, weights, or filter. Okay, then we apply this on this, apply this on this, and apply this on this. All right, and this filter is going to be there common for all of the values. This filter is going to be common for all of the values in the layer. This filter is going to be common for all of them. So it's basically a single filter, and it has basically different values for different channels. Okay, is it making sense to you? So all we did was, first of all, we multiply this with this, xijk with wuvkk, this with this, this with this, this with this, and we multiply all of them in the same way, right? And then we sum it up. We sum up these values. Here, we are first summing up the values across the layers. That means this, this, and this. We are summing up these values first. And then we are summing up for each of the v value that may be like horizontal value for each of the columns, whatever we get. And then we sum up for each of the heights, and then we get the final outcome. Question from Binta is, does UVK follow permutation or combination? UVK, what is UVK? U means for each of the window, right? Since the filter has how many values? Filter has, this is U, this is V. This is U, this is V, this is U, this is V for different K dashes. Okay. So I'm not able to follow that part. Does UVK follow permutation or combination? So UVK are basically, this weights is nothing but 4-dimensional vector. We have set of weights for each of the feature maps in the output, like we had horizontal and vertical strips. Then out of that, we have one set of weights for each of the input layers. That is for K dash. K dash means input layers. K means current output feature maps. And U and V means the values of the, generally this is basically WUV. For K dash equals 1 and K is 1. Okay, so right now we are only dealing with K as 1, as in there is only one map here. There could be multiple such maps over there. Okay, so this is nothing but a for loop of, okay, so this is nothing but a for loop of big for loop. Okay, and we will do this again for every value of K, meaning if you have, okay, again, I'll just take you back if you have missed on this part. Okay, so this is ZIJK. This is ZIJK. Okay, then this is FH. This is FW. Right? This is the receptive fields dimensions. Then this is K. This is, so I'll go back here. Right. This is the output we are saying. This is the input layer for this. These are K number of feature outputs, and these are K dashes. Okay, and right. So we have X I dash J dash K dash and X I dash J dash K dash for these, right? So all of these values are used to compute the next layer. Okay. So this is W. This is the filter map that we are applying. Okay. Right now we are just thinking about these two layers. We are ignoring this part. We can actually do the same thing here also. So you can think of it WUV. KK is this filter, right? This is the values of the filter map, WUV. These are the weights. There will be weights for this, weights for that, right? So these are K such filters, and these are K dash number of layers. Okay, these are K dash number of layers. These are K. Okay, that's what is happening. So for each ij, we first find out who are the corresponding pixels which are going to be combined to form this. All right, that's what is happening here. So we are summing up, we are multiplying each of these pixels with the feature map, with this feature map. We are multiplying each of these these features. So we are multiplying each of the pixels or each of the values of neurons with the feature map in every layer. Then we are computing the summation of all of the values, and then we are adding a bias term. This we are doing for all of the ij and k, all of the ij and k in this layer. For this, then we'll have many pixels here. All of these pixels are going to be composed of the summation of these values, just like this. Okay. A question from Binta is, could you have an expression for zijk? This is the only expression I could think of. It's nothing but summation of all the values. It's like in the other example is that you can think of this value as the volume of all of this huge cube that you see. This one is the volume of the whole cube. Okay. And how are we computing? The only difference is every point in this image, in this particular surface, we are multiplying with certain weights to compute the weight of each layer. Okay, that's how you can think of. So we are computing the volume of the whole layer into a single value. And how are we computing? Using this kind of a formula. All right. Okay, this one shows exactly how the computation is going on. And this one shows the animation of, say, these are the input layers. There are multiple input layers. And this is only a single feature map in the output. And this is our filter that has, say, 3 parts to it. Okay, these are the feature weights, the filter weights. And then we are applying these filters on each individual input layers and computing the total. All right, is it clear? Then here there is a bias term. All right? No? Any questions? Balaji, Bintao, Gigi, James, Pavan, Shahrukh, Prateek, Shiva? No question? Should we move? All right. Okay. A good question. So a question from Bintao is, the for Z00, let's say this is Z00, okay? And we have, say, bias term same for all, like 1. Then we are, say, 00, as in this is 0, okay? So for Z00, we have to compute all of the values, right? All of the values. So what we have to do is say this is our this is one filter. This is another. This is a part of the same filter actually, or you can say feature map. So here you can see. So let's say here we are saying JAD 0, 2, JAD 0, 2, and 1. This is what's happening. Z 0, 2, and say K equals 1. Right now K is only 1 because there's only one output layer. And so what's happening here is we are computing all of this. We are multiplying, first of all, this with this, this with this, this with this, this with this, and then we are summing it up all. Okay. And then we're multiplying parallelly these values, and then we are summing it up. Then we're multiplying this with these and summing it up. So the summation of this one gives us 314. This one gives us minus 175. This one gives us 326, and we are adding 1 to it, right? So I think that'll be it. So there'll be how many values? 9, 9, 9, 20, total 27 values after this. Okay. So this one goes from 0 to 3, 0 to 3, 0 to 3, and 0 to 3. So 3, so 3 into 3 into 3, that is 27. So total 27 terms will be there where values are being multiplied, right? Okay. So I think this is basically the example of how do you fill the parenthesis. So these terms, which are being summed up here, there'll be 27 such terms. All right. All right. So we could do this really easily. And the only reason we have, if you think about it, the linear algebra, why we use it again and again, is to avoid these for loops, right? For loops become really confusing after a point of time. And it's always difficult to carry so many variables using either array, either we use arrays, or if we use variables, it becomes impossible. Therefore, the linear algebra is essentially the operations on arrays that makes our life easier. So if we have to implement the same thing using TensorFlow, it'll look far more easier than this expression. This expression kind of intimidates. So in TensorFlow, each input image is typically represented as 3D tensor of the shape of height, width, and channel, the 3 dimensions. It has got some height, it's got some width, and it has got some channels, right? That's basically the input image representation. The mini batch, a mini batch is represented as 4D tensor of the shape. When we are training a neural net, we generally train on a small mini batch. Okay, instead of training it on whole of the batch, we would generally train it on a smaller batch, because training in a single shot for the whole batch is not possible, as you will see later, because of the memory constraints. So we generally train on a mini batch. So the input is generally the input is generally represented as a 4-dimension vector, 4-dimension tensor. First one is minimum batch size. For each of the images, we have height, width, and channels. Okay, so total number of pixels, total number of pixel values is going to be total number of pixel values is going to be this multiplied by this, multiplied by this, multiplied by this. If we had only height and width, and it was a grayscale image, so total number of pixels will be height into width. But since we have RGB channels, so total number of pixels are going to be height, width, and channels. Total number of pixels or total number of neurons in the input input layer are going to be minimum batch size multiplied by height multiplied by width and channels. Yes, channels are RGB. That's correct. 3. So channels in our case is going to be 3 if it's a colored image. If it's a satellite data, the channels are going to be say 4. All right. So the weights of the convolutional layer are represented as 4D tensor of this shape. So right. So for each of the layer in the input layer, for each of the layer in the output layer, for each of the height and width of the field is what is the weights. Okay, so weights is a function of the coordinate. So the fh into fw, that's height of the field multiplied by width. These many weights are going to be there for each input layer and for each output layer. Correct? This is how big our filter was, right, when we were applying on 2D objects. So fh by fw. But since the input layer could be many, so we have many such filters. Similarly, there could be multiple output filters, right? And so there could be these many weights, of convolutional layer. Now, the bias term of convolutional layer are simply represented as one-dimensional shape. Why? Because it is not a function. It is basically fixed for entire computation of per input layer per field. So for whole of the field applied on every input layer, we have only one single value. And since there could be n such filters in the output layer, therefore we have these many terms. So here the bias term is fixed for all of the output layer. If you have many output layers, why will we have many output layers? Maybe we are applying multiple feature maps. Okay. So this one is a single dimension tensor, right? Okay, so let's take a look at the sample. The following code loads 2 sample images using scikit-learn's load sample image. It loads 2 colored image, one of the Chinese temple and other is a flower. And so we are just importing, say, NumPy, and then importing the data sets. Then we are converting this into an array. Okay, and here it's essentially a multidimensional array, and the shape of this data is actually having 4 dimensions: batch size, height, width, and channel. All right. Then we create 2 7x7 filters, one with vertical white line in the middle and other with a horizontal white line. And how do we do that? By first filling up everything with zeros, then setting up, say, the x-axis or the y-axis. So for the first filter, let me again go through this one. So here we are creating a vector of size 7 by 7. It's a vector of size 7 by 7. Why are we doing that? We want to create 2 filters, each of size 7 by 7, having 3 colors. Okay, here channels is equal to 3. And there are 2 filters. So basically the filters test is equal to 7 by 7 into channels multiplied by 2. That begin a NumPy array. Then for all of the values in the 3, as in for all of the 0, 1, 2, 3. So basically the 4th column we are putting as 1. Okay. For 4th column in the first filter, we are marking it as 1, while 4th row in the second filter, 4th row in the second filter, we are marking it as 1. Okay, since it is based off 0, therefore this is fourth row, this is fourth column, this is first filter, this is second filter. So we are filling that those with 1, and then we have basically converted that into a TensorFlow constant. Okay, whatever filters we have generated using NumPy, we create that as a TensorFlow filter. All right, so let's just move to the notebook. Okay, so git pull. Okay, so let's just move up here. So run the setup part. Setup part has the basic functionality of importing and defining the default functions. Then plotting the image also, we have created a function, and of course import the TensorFlow. Okay, now we are basically loading China and flower, two images, and then okay, so here, all right, we are just picking some part of the image. Okay, right, we're just picking part of the image. And here, how does China look like? We could say plot image, plot underscore image. Okay, this is the complete image. And this image that we are using looks like this. So we are just taking part of the image. I think probably from here. Okay, so out of this image, we are just picking part of it. And this is the one. Okay, a question from Bintao, where does future come from? That's basically to keep it backward compatible for Python 2, so that we get the print function, division, and Unicode literals. Okay, further, we have loaded the image and the flower. Flower also we can check. How does it look? Okay, and then here we are converting this China image into, we just picking up a small part of it. Also, the image shape or size is something you can take a look. So it has 3 channels. It has this dimension, okay? And here, so if we are, okay, so we can actually, okay, so we are converting this image. We are removing the color part of it, and let's take a look. So you can see the color is gone from it because we have deleted, we have changed the channels to 1. Okay, we've changed the channels to 1. All right. Then at this point, we are creating, what? We are creating, we are filling it with zeros. First, the first thing we do is we're filling it with zeros. Then we are setting this with one of the columns we are setting as 1, and then one of the rows we are setting as 1, and then we are going to see how it looks. Okay, so this is our vertical slit, or you can say vertical filter. This is our horizontal slit or horizontal filter. Now, okay, to take a look at exactly how does it look like, you can use the fmap, and there are so many dimensions in this. You can see now. A question from Binta is, flower.shape gives us three values. This is what? This has 3 dimensions, right? That means its resolution is 427 by 640, and it is colored image, so it has pixels in 0, pixels in 1, pixels in 2. Okay, in all the three dimensions. All right. So if you basically remove the third one, it'll become a black and white image, provided you have the numbers representing other values as well. So its height is this much, width is this much. It has 3 colors, R, G, and B. That's what it represents. Okay, so once we have done that, we are creating, say, constant out of the feature maps, the filter maps that we have created earlier here. These are the feature maps that we have created. Now we are creating a TensorFlow constant out of it. Where is the, yeah, here. So here, this is our, again, we are resetting the graph just like we usually do. And then we are defining capital X. Capital X is batch size, meaning number of instances, which is none, meaning it could be anything. Then height and the width. Okay, so the X has got height, X has got width, and we are feeding a gray image. Okay, grayscale image. So that's our input data. Then input data X, which will feed when we train. When we run our model, then when we train our model, then we'll be feeding X. Now we're defining a constant out of the feature maps, or you can say the filters that we have created, horizontal and vertical, both in a single shot. This feature map contains both filters, horizontal as well as vertical. Then we are using a function called tf.nn.conv2d, to which we are passing the input data, we are passing the feature maps, and we are also informing it about our strides pattern. Strides pattern. Out of this, ignore the first value and last value. This one is horizontal stride and vertical stride. Okay. And whether we want to append the padding or not, that's controlled by this particular one. If we have padding equals same, that means on both the sides, on all of the sides, the paddings will be same. Otherwise, we could have padding as none. Okay, so here we are basically while running the session, we are evaluating this one. Again, as somebody has asked yesterday, we could either say session.run, or we could actually say the same thing just like this one with session.run, and we will get the same results. Okay, so you can see, so it has basically applied. No, it has not applied yet. Okay, yeah, these are the input image. Then this is the output image. This is the output image that we have applied. So this is the input, this is the output. And there could be 2 outputs, right? One is horizontal and one with horizontal one, and other is vertical. All right. So the one which has, see these lines, is vertical more. Okay. This one is a vertical filter, while this one has more horizontal lines. This one is a horizontal filter. Is the result of horizontal filter. All right. So yes. So this is what we have done just now. Now let's look at the simple example. Apply them to both the images using the convolutional layer built using TensorFlow's 2D conv2D function. All right, so we did this part, right? Let's go into more details, and we have already done it. Now let's try to understand the previous code. So what we did was we first of all created X as the input for our model. It's a mini batch, mini batch, and filters is the set of filters to apply. Again, filters also is a 4-dimension vector. It has filters will have the values of weights for values of weight like in X and Y, as well as in for each input layer and for each output layer. Okay, so it could have multiple filters and so on, right? Stride is a 4-element 1-dimension array where the 2 central elements are vertical and horizontal strides. These ones you can ignore for now. The first and last stride must currently be 1. They may one day be used to specify a batch stride to skip some instances. Okay, it's not yet implemented. And a channel stride to skip some of the previous layers, feature map, or channels. Okay, so we have a channel stride to skip some of the previous layers, feature maps, or channels. All right, now the padding could be either valid or same. Right now we are using same. If we set it to valid, the convolutional layer does not use 0 padding. Okay. If we do not use if we use say valid as the value here in the padding, then it won't use the 0 padding at all. Okay. It'll basically may ignore some of the rows and columns at the bottom and the right of the input image, depending on the stride. If it is set to same, the convolutional layer uses 0 padding if necessary. All right. So padding. A question from Pratik is why filter is a 4D tensor, right? So let me go back. Right. So filter basically is 4D tensor. Why? Because there are 2 filters. One is horizontal, one is vertical. That's defined by the last dimension. And rest is it's an image. It's an image, right? So this is the dimensions of the image. These are dimensions of X and Y, right? In the form of X and Y, these are the dimensions. And this one is 1 per channel. So the filter is 2D 2-dimensional weights. And it is for each channel in the input. And there could be multiple such filters, and therefore the 4th one represents that multiple. Okay, that's right. So this is going to be 3. It's going to be 3. All right, let me show you. So yeah, in the input image, yeah, that's a very good observation. Actually, what we did just now is we converted the channels into 1. I'll show you how. Here at this point, we converted the channel into 1 here. So we converted the input image into grayscale. You see that? Therefore, this image is a grayscale, and therefore if you see this one, the filter is basically again gray, and it's going to be same across all the channels or layers. Okay, x is equals to 2 means on the color axis, we basically, okay, so we are computing just the mean across the third axis, which is the color, okay, and computing that basically out of the three dimensions like R, G, and B, it's computing the mean of red, green, and blue, and just putting that as the final value instead of the three vectors. So it's converting that into, then it is resizing that. Okay. So this is how we can convert an image quickly with a quickly to the grayscale. All right. I'll just delete this portion. Okay. All right. So where is it that we are filling the feature maps? I think this is where we're filling the feature map. Yeah. So here the channels is actually one. See, channels is actually one. It's not channels here. Okay, it's actually one. Okay, this is right. That's why. All right. So all right. So when we say padding equals to valid, for simplicity, only the horizontal dimensions is shown here, but of course the same logic applies in the vertical also. Okay. So let's say this was our sliding window, or this was our receptive field. So we are moving it. We'll keep on moving from here. We'll start from moving here, then here, then here, then here. And while we are about to reach, and if let's say, let's say we are moving by 2 every times, or let's say we're moving by 5 every time. So it will only move till here. It'll ignore these parts because next one will go outside, right? So in these cases, when there are strides more than one size, the chances of at least one of the values being ignored is there. So padding equals to valid means don't overflow at all. Instead, choose to drop some of the input values. Okay. Okay. While the padding equals the same as in, we start with the, so in this case, the number of output neurons is equal to the number of input neurons divided by strides and rounded up. Then zeros are added as evenly as possible around the inputs. Okay. So basically the here the number of neurons is 13 and stride is 5, hence the number of output is going to be 3. All right. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? 13. So 13 by 5 is some decimal number, and we compute the upper value, that is 3. So we have say 3 here, and stride is 5. So it's going, the input value is going to be 3 into 5, right? That is 15. So we need 3 more values here. Okay, 3 more values here. So we basically put paddings on both the sides. All right. So this is one way of putting the paddings. All right. So if the stride is not 1, then these kind of things might happen. Right. Here stride is 5. So the input value should have been a multiple of 5. Therefore, we needed to add some more values. Okay. All right. A question from Bintao is how about axis 0 and axis 1? Axis 0 means all the coordinates, x coordinates. Axis 1 means y coordinates. And axis second, x equals to 2 means the color. Okay. If we do the same thing what we did with the color, what will happen is the image will be, if we let's say do the same thing across axis 0, what we did with axis 2, then what will happen is all of the values will be same across all of the x-axis, right? Will be same horizontal line repeated again and again. All right. A question from Vinta is, what is RC parameter and PLT RC parameter? That's for plotting. Okay, that's for plotting, right? So here basically just to show how big should be the label sizes, we are specifying these. Okay, we are specifying these parameters for the plot in order to display the label size. This is X tick label size and this is Y tick label size. Okay, this is X tick label size and where it is going to be displayed. Okay, so these are the default properties that we are using, and we are just fixing the label sizes. All right. We'll see that once we have some labels. All right. Now, the CNN hyperparameters. The CNN layers have quite a few hyperparameters, right? This is something that we discussed. We must choose number of filters, their heights and widths. We must choose the stride sizes, heights and widths, and the padding type. Okay, whether we want to use the valid or the same. As always, you can use cross validation to find the right hyperparameter, but it is very time consuming. Okay, so while the values weights of each filter is basically trained, as in it comes from training, the number of filters is something that you need to decide. All right. One advantage with CNN is that the convolutional layers require one downside, actually not advantage, require a huge amount of RAM, but it is better than the fully connected ones. Okay, so the downside of one disadvantage of CNNs is that it consumes a huge amount of RAM, specifically during training, because even though while we are predicting using the CNN, we can drop the values of previous layer once we are done with that. But during the time of training, we need to retain these values. We need to retain these values of X and Y's and the various layer values, because the reverse pass of backpropagation requires all of the intermediate values. Remember when we were doing backpropagation, we needed all of the values in order to compute the gradient, right? So backpropagation needs the various values. Therefore, in the forward pass, whatever values we compute, we retain. We can't drop it in between. While at the time of testing or running the model, we don't require that much of memory. So consider the CNN layer with 5 by 5 filters. It will be, and let's say we have 200 feature maps, each of the size 150 by 100 with the stride of 1 and same padding. So if the input image is of 150 by 100 RGB image, let's say the input is 150 by 100 RGB image, 3 channels, then how many weights or parameters are going to be there? Anybody? How many weights are going to be there here? What was the dimension of the weights? The dimension of the weights was the size of the filter multiplied by total number of input layers and total number of output layers and so on. Anybody? How many parameters would be there? All right, so we will take a break here today. We will continue from here in the next session. In the next session, we will do more exercises as part of it. The core of CNN, this was the core of CNN, understanding the structure, is clear, as in you will have, now you will be able to understand the code and the remaining part. We will continue from here. We will do an implementation of MNIST with a high accuracy and see how it goes. All right. So see you next week. In the meantime, give it a thought. We will continue from this question in the next session. All right. Thank you, everyone. Thank you for paying attention. And I look forward to see you next week. Okay. So thank you, Prateek. Thank you, Gigi. Thank you, Balaji. I'm happy that you find the session great. Thank you, James. All right. Please keep asking the question, and that's the only way to learn. All right. Bye-bye. Have a good day. Thank you, everyone.